Good evening, everyone. We are from Team 10 that consists of Arista Ambari, Aurell Choirunnisya, Keyla Fauzia, and also Syifa Nur'aini. And today we're going to present our fourth assignment on PVT experiment. So this presentation will cover about PVT experiments in general, including their objectives, theory, and also workflow. So let's just begin. Okay, first of all, we're going to discuss about the objectives of the PVT experiment and how the information we obtain plays a crucial role in reservoir engineering. So, a pivot experiment is basically conducted to analyze the behavior of reservoir fluids under different pressure and also temperature conditions. So, the data collected from this experiment is essential for first, evaluate reserves that helps us to understand the amount of recoverable hydrocarbons in the reservoir. Second, to develop the optimum recovery plan that helps us to design the efficient extraction strategies based on fluid properties. And third, to determine the quantity and also quality of produced fluids that helps us to analyze the composition and also phase behavior of reservoir fluids. So the information that we gather from this PVT experiment is critical for several key calculation and also design, including material balance calculation, production performance calculation, design of surface facilities, reservoir evaluation, design of development processes, well test analysis, numerical reservoir simulation, and also design of enhanced oil recovery or EOR process.
Okay, so next I will explain about an oil reservoir, which is a natural underground formation where crude oil accumulates within porous rock over millions of years. These reservoirs form as organic material transform into hydrocarbons next and get trapped by geological structures. Then these are four key characteristics of an oil reservoir. First is reservoir rock. This is the porous medium that stores oil, such as sandstone or carbonate rocks. Second was reservoir fluids, which is a mixture of oil, gas, and water exists in varying proportions within the reservoir. Third was reservoir pressure, which is this determines how efficiently oil can be extracted from the formation. And fourth is reservoir traps. This can be structural, like faults, or which is help prevent oil from escaping. Then this characteristic is essential for optimizing oil recovery and ensuring efficient production strategies.
Now I explain about the gas reservoir. A gas reservoir is a subsurface accumulation of natural gas trapped within a porous and permeable rock formation, sealed by an impermeable cap rock that prevents gas from escaping. This reservoir formed over millions of years through the thermal decomposition of organic material under high pressure and temperature. Now, the difference between oil reservoir and gas reservoir. The aspect hydrocarbon phase. Oil reservoir is contains liquid hydrocarbons or crude oil and may have dissolved gas, whereas gas reservoir contains gaseous hydrocarbon natural gas with little to no liquid. Next, fluid property. Oil reservoir higher viscosity and density is making flow slower, whereas gas reservoir lower viscosity and density making flow easily. The last one is recovery efficiency. Oil reservoir is lower recovery, whereas gas reservoir is higher recovery.
Okay, so next we'll discuss about collections of fluid sample. First one, objectives. Reservoir fluid sampling is essential because 1. To prevent gas breakout from oil. If pressure drops below the bubble point, gas will separate from the oil, altering the original composition. 2. To prevent liquid dropout from gas. Gas in the reservoir may condense into liquid when pressure and temperature decrease, changing the fluid properties. Last, because the gas to oil ratio or GOR and composition change if sampling is not done correctly. The GOR measured at the surface may not reflect the actual reservoir conditions if gas escapes during the production. Next, the quality of the obtained sample depends on several factors, such as 1. Reservoir conditions. Pressure, temperature, and fluid properties in the reservoir affect sample quality. 2. Well conditioning. The well must be conditioned to avoid contamination from the drilling fluids or previous production. 3. Sampling methods, equipment, and procedures. Selecting the appropriate method ensures that the sample remains representative. Lastly, human factors. Errors in sampling, transportation, or analysis can lead to inaccurate data. The reservoir fluid sample must have the following characteristics. First, fluid remains under pressure or a pressurized fluid. To maintain composition as in the reservoir, the sample must be stored under the high pressure. Second, oil with all gas in solution. If gas separates from the oil properties will change and no longer represent the original reservoir condition. Lastly, gas with heavy components remaining in the vapor phase. If the pressure drops too low, heavy components in the gas will condense, altering the gas composition. Fluid sampling should be conducted at the right time to obtain the most accurate data. So, when should sampling be conducted? As early as possible in the reservoir's life, before significant pressure changes occur due to oil and gas production. Before pressure drops below the saturation pressure, if pressure falls below this point, gas will begin to escape from the solution, changing the fluid properties. In general, there are two main methods for reservoir fluid sampling. First one is downhole sampling. The sample is taken directly from the wellbore under the reservoir pressure and temperature conditions. This ensures that the gas remains dissolved in the oil or formation water, preventing compositional changes due to gas breakout. There are several advantages of downhole sampling, such as provides the most representative sample of reservoir conditions and prevent phase separation of gas and liquid during the sampling. So there are several equipment that we use for downhole sampling, such as SRS and MDT. SRS, single phase reservoir sampling, is a sampling tool with a buffer fluid mechanism to maintain the pressure. An MDT, Modular Formation Dynamics Tester, is a system used in wireline logging to collect fluid samples from the wellbore. We can take a look at the picture on the right. Next, the methods of reservoir fluid sampling is recombinant sampling, or we can call it surface sampling. Production fluids that have undergone separation at the surface are recombined with the correct gas-to-oil ratio to match the reservoir conditions. There are several advantages of this sampling, such as easier to conduct than downhole sampling and doesn't require specialized downhole equipment. So the equipment that we use for the sampling, starting from left to right, there is wellhead. The function is to control fluid flow from the well. Next, we have separator to separate oil, gas, and water. And above, we have gas meter, measures the volume of gas leaving the separator. And below the gas meter, we have gas sample cylinder, collects gas samples for analysis. Below the gas sample cylinder, we have oil sample cylinder to collect oil sample for analysis. And on the left, we have water sample cylinder to collect water samples for the analysis. Lastly, on the right, we have stock tank to store separated oil before the transportation.
Then, about oil versus gas concentrates. These two are hydrocarbons fluids found in reservoirs, but they exhibit different characteristics under varying pressure conditions, which oil exists as a liquid in the reservoir with dissolved gas, and as pressure decreases, gas is released. Then, with gas concentrate, on the other hand, exists primarily as gas with some liquid components, and as pressure drops, more liquid concentrate forms. Key differences included first is the critical pressure point, which oil reaches its bubble point pressure, while gas concentrate reaches its dew point pressure, and the production challenges and oil experiences gas liberation, which reduces its volume, whereas gas concentrate suffers from liquid dropout, which affects gas deliverability, and the behavior with oil releases gas as pressure declines, whereas gas condensate forms more liquid as pressure drops.
For the next one, I'm going to explain about the routine PVT analysis, which consists of several important laboratory tasks that help us understand the behavior of reservoir fluids under different conditions. So these tasks are essential for reservoir engineering, production, optimization, and also forecasting. For the first task is called constant composition expansion or CCE task. So this task is conducted at reservoir temperature to determine important properties such as bubble point pressure and also oil formation volume factor. So the sample is expanded at constant composition while reducing pressure to observe phase behavior and gas liberation in a closed system. And this task helps us in understanding the compressibility and also volumetric behavior of the reservoir fluids. For the next task is called differential liberation or a DL test. So unlike the CCE, in this task, gas is removed step by step as pressure decreases, allowing us to study the fluid's expansion behavior. So it provides critical data such as solution gas oil ratio or GOR, oil shrinkage, and also gas formation factor at various pressure levels. So the result in this task helps in predicting how much gas will be liberated and how the oil will behave as pressure declines. For the next one is called a separator test. So this test is performed to simulate how reservoir fluids separate into gas and liquid at surface conditions. So the well stream is passed through multiple separator stages at different pressure and temperature. So it helps in optimizing separator condition to maximize liquid recovery and also improve surface processing efficiency. And as for the last test is called constant volume depletion or CVD test. So this test is used primarily for gas reservoirs as is performed at constant volume while reducing pressure in stages. So the goal is to determine gas condensate behavior, liquid dropout, and also recovery efficiency as the pressure declines. So this task is essential for designing production strategies in volatile oil and also gas condensate reservoir.
Okay, so next we will discuss about the experimental flow diagram. We can take a look at the left picture. It's a compact PVT cell for black oil and gas condensate samples. This figure demonstrates a compact PVT cell designed for small volume PVT thermodynamics properties and phase behavior studies of black oil and gas condensate samples. So below the picture, we can see the flow diagram starting from the PVT cell and then high pressure pump. Next, the control panel, and lastly, the data acquisition system. The first equipment or process is the PVT cell reservoir condition simulation. It composed of an efficient fluid mixer mounted on the piston, a visual head, an accurate pressure transducer, and an electric heater for homogeneous temperature control. A sapphire window and digital camera system allow real-time monitoring of the gas-liquid interface, especially during the differential vaporization or flash liberation. The cell's position can be adjusted, upright and inverted. For the upright one is for oil studies and the inverted one for the gas condensate experiments. Next, the high pressure pump, the fluid pressure control. It generates pressure up to 10,000 psi using either a constant flow rate or a constant pressure method. It injects fluid into the PVT cell with high precision. And then we have the control panel, the system operation. It manages power, lighting, the stirrer, and the temperature settings. The control panel ensures that experimental parameters are maintained as required. Lastly, we have the data acquisition system, processing and analysis. This system uses specialized software for calibration, test selection, and experimental data analysis. It displays results in graphical form to determine bubble point pressure, dew point, and compressibility factor, or we can symbolize it as Z. So the conclusion of this experimental flow diagram, The PVT experiment enables high precision characterization of reservoir fluids. The system works synergistically to control, monitor, and analyze fluid behavior under different pressure and temperature conditions, providing crucial data for optimizing oil and gas production.
Now, moving on to the experimental workflow for PVT analysis. PVT analysis is essential for understanding the behavior of reservoir fluids under different pressure and temperature conditions. The process consists of several key steps. The first one is sample collection and preservation. Is obtaining a representative fluid sample from the reservoir while maintaining its original pressure and temperature condition. The second one is sample validation and preparation. The collected sample is then checked for contamination and prepared for testing. Next, constant composition expansion. This test is conducted to determine the bubble point pressure for oil or the dew point pressure for gas. Next, differential liberation test. This test simulates the behavior of oil as pressure decreases, helping determine gas-oil ratio and shrinkage factor. Next, constant volume depletion. For gas reservoir, this test evaluates phase behavior in gas condensate systems as pressure declines. Next, separator test for oil and gas reservoirs. This step simulates the separation of oil and gas at surface condition to optimize recovery. Next, viscosity measurement is measured to understand its flow characteristic. Next, equation of states modeling and data interpretation. The collected data is used to create a thermodynamic model that predicts reservoir fluid behavior. The last one is reporting and application in reservoir engineering to optimize reservoir management and production strategies.
Okay, so that's all about our presentations. These are the references that we use. Thank you for listening. Wassalamualaikum warahmatullahi wabarakatuh.